So in the last video I was not able to do a question correctly. What I was thinking was that the internal forces, they don't contribute any work, and that's true. In a rigid body that does happen, that the internal forces do not do any work. But in case of non-rigid body, we have a different condition. So for a rigid body, for any body, torque due to action reaction pair is 0, so the angular momentum does not change due to that action reaction pair. In short, the internal forces cannot change the angular momentum of the system, but they might change the energy. So the increase in rotational kinetic energy is the work done due to the torque given by this formula. So we use this, actually we kind of proved this formula in a proof for T equals to I alpha. Yes, actually, yeah, in the first proof, that is for rotating bodies only, which are not translating. So here's the proof, just in a short kind of way. Okay, so here the work done by Fr is 0, as there is no displacement in radial direction, because this is a rigid body. So the radial direction, yeah, that distance is fixed. Actually distance of every point from every other point is fixed on the rigid body, and hence that work is 0. But for a non-rigid body, the radial part also does work. For example, this is one of the questions which were really nice and gave me a lot of conceptual clarity. So this is a nice example. So here's this very thin hollow tube from which a very thin thread is passing, and that thread is attached to this point mass of mass m, and then this mass is rotating like this in a circle. So this circle has radius r1, and no, there's no gravity, there's nothing like that. It's almost as if it's in space, right? And this thread is held on by somebody, I don't know. So yeah, this is basically like a rigid body, because this distance, it does not change, and well, m is in fact a point mass. So cool. So the torque due to T, so T is the tension over there, the torque due to T on the rotating system is 0. And by the way, because we are holding it like stationary, so this hollow tube is stationary, so we are not doing any work on this. We are just providing the normal force to keep it stationary basically. So that's out of the way, because there's no chance that from there any kind of work would be generated. No. So the torque due to T on the rotating system is 0 when taken with respect to C. So that's evident because the torque is directly in the radial but the force T is directly in the radial direction. It doesn't have any component in the tangential direction. So the torque is 0, which means that the angular momentum is conserved. So suppose I pull this thread and this radius reduces from r1 to r2, then the angular momentum will be conserved, right? Because throughout the whole process, when I'm pulling it, I can only pull it in the radial direction, so that does not create any torque. So the angular momentum is conserved, and we have m r1 squared omega 1 equal to m r2 squared omega 2, okay, which means omega 2 is r1 upon r2 squared omega 1. But by pulling the thread, we did some positive work on the system, so the new rotational kinetic energy, it should be more than the previous one. So if we take the ratio of the previous kinetic energy to the new rotational kinetic energy, so notice that I1 omega 1 and I2 omega 2 are actually just the angular momentum, and they are equal, so they cancel away. So just get omega 1 is to omega 2, and we know that omega 2 is r1 upon r2 squared omega 1. So putting that over here, we get this ratio, 1 is to r1 upon r2 squared, and since r1 is bigger than r2, this is going to be 1 is to some number which is bigger than 1, which means that the new kinetic energy is actually bigger than the previous one. And this is obvious because we did some positive work, right? So this is coming over there, and we are also pulling it in that direction, so we did some positive work. So now this is the example which was confusing, and yeah, so suppose this is somebody who is standing on this rotating plate. Initially it's rotating with omega 1, so the angular momentum is going to be I1 omega 1, and it's going to be conserved because there's no external force on this. There are only internal forces, and internal forces always conserve angular momentum, at least, yeah, that's true. Okay, so this angular momentum is I1 omega 1, which is also I2 omega 2, and I3 omega 3. In these cases it moves with omega 2 and omega 3 angular velocity. So over here the forces are acting something like this. So there's this radial force, right, the force in the radial direction. So basically this is the axis of rotation. So you can see that this direction is actually the radial direction. The other two directions, this thing and the one which is upward, these are tangential. Okay, wait, yeah, so this is coming out, correct. So over here you have this force which is coming out of his arm. There's some force which is going down. So these two are tangential and they don't do any work. Okay, so the DFR part does some work in this case as the point of application. So this point of application is moving, right, and the force is doing some positive work. So now I1 omega 1 equal to I2 omega 2 equal to I3 omega 3 equal to L, we know that. And because I1 is bigger than I2 is bigger than I3, why is that? This is more spread out, right? So the summation of mr squared, well, since more of them, right, so more of these masses have bigger r, thus this moment of inertia is going to be bigger than this case, and this is somewhere in the middle. So this has the biggest moment of inertia, this has the least moment of inertia. So I1 bigger than I2 I1 bigger than I2 bigger than I3, thus omega 3 bigger than omega 2 bigger than omega 1. And if we calculate the kinetic energy ratio or whatever the relation it should be, so yeah, L is the same thing for all three. So we can say this relation is true based on this relation. And notice that this thing is just the kinetic energy. So putting L equal to I3 omega 3 into this thing, you just get half I3 omega 3 squared, which is the kinetic energy. So from this we get kinetic energy 3 is bigger than kinetic energy 2 is bigger than kinetic energy 1. So this is the kinetic energy where you initially had no work done by the force Fr. Then after that some work was done, some positive work was done by Fr, as Fr is in direction of radial displacement. So thus we get like K2 is bigger than K1, and then after that even more work was done, so K3 bigger than K2. So the main reason for this extra kinetic energy in the system is that the extra kinetic energy comes from the man himself. It's from his muscles, from the chemical potential energy stored in his muscles, which gets used up as he pulls himself towards himself, right, so towards the axis basically. So yeah, that's it. Have a nice day.